Okay, so we're now going to look at the graphs of tangent, cotangent, cosecant, and secant functions. Let's begin with the graph of tangent and cotangent. Now we have already discussed domain and range of these functions in earlier sections of chapter 6. So this time we're just going to get the same information, and by information I mean like things such as a range, domain, zeros of the functions or the x-intercepts. We can get these from the graphs of these functions. So let's begin with the graph of tangent. Okay, so here we have tangent function. We're looking at the basic graph for all of these without any sort of stretch, compression, or shifts of any sort. So the most basic form, y equal tan x. The period of this function is going to be pi. That's one complete cycle of tangent. Okay. Now, let's take a look at the graph of tangent. The graph of tangent is going to look like this. And again, I'm assuming that everybody has seen these before. We're just kind of quickly recalling what these graphs look like. Okay, so here's one cycle of tangent. Of course, the function is periodic, so we do recognize that the other portions most likely go like this. And of course, remember, these are periodic, so that pattern goes on indefinitely in both directions. All right, so the asymptotes for the first cycle lies between negative pi over 2 and pi over 2. That will give you in the first set of vertical asymptotes of the graph of tangent. And let's see, the general equation for the vertical asymptotes of tangent. Now, if you recall tangent, by the way, as a ratio of sine to cosine x, right? The ratio identity. This will actually help me write the general equation for vertical asymptotes and the zeros of the function. The vertical asymptote of tangent are places where you divide by 0. That means cosine x is 0. So what's vertical asymptote of tangent becomes zeros of cosine. And the zeros of cosine are going to be at pi over 2 plus k pi. Remember, in all of this section, I'm just going to say it one time, k is an integer, so we don't have to do this every time. K is an integer. All right, so the vertical asymptotes. Now, these are the places where the function is undefined. Therefore, we can actually, from the vertical asymptote, get the domain. Domain of x is all numbers except the vertical asymptotes. Places where cosine, the denominator of tangent, is 0. All right. The other thing we are interested in here are the zeros. Very important. The x-intercepts, because those become, when we solve the equations, these become solutions to the equations, trig equations. The zeros of tangent occur when the numerator of fraction, that means sine x, is 0. So the zeros are going to be x equals to k pi. These are zeros of sine k pi. And you can see, for example, right here, 0 is an x-intercept, which is when k is 0 in my k pi form. All right, and what about the range? The range of tangent, you can see, and again, we showed this earlier. In fact, I proved what the range is, but from the graph, you can see the range goes from negative infinity to infinity. These are the y values of the function. All right, and there you have it. So one cycle, the period is pi, and the vertical asymptote from negative pi over 2 to pi over 2. One at negative pi over 2, the other at pi over 2. So we're going to stay with this throughout the next three, the graphs of the next three trig functions. If there are vertical asymptotes, we want to indicate them. We want to find range, domain, and zeros of these. So that's for tangent. Now for cotangent, I'm going to do very similar to tangent. Cotangent. Now for cotangent, that would be y equal cotan x. Now the ratio identity for cotangent, that's the ratio of cosine x over sine x. Therefore, the vertical asymptotes of cotangent are places where sine is 0. That means x equal to k pi. And that leads to the domain of the function. The domain, therefore, is all real numbers except what makes division by 0. Places where you have vertical asymptotes. The range is going to be negative infinity to infinity, and I'll show you that in the graph. What else? We got vertical asymptote, domain, range. Oh, zeros, very important. The zeros or the x-intercepts of the graph, those are the zeros of cosine. These are where x is pi over 2 plus k pi. Places where the numerator is 0 of that expression. Now, what does the graph looks like? So this time, one cycle of the graph of cotangent looks like so. The vertical asymptote is going to be at x equals 0 and x equals pi. The intercept is at pi over 2. Okay, then that will be again one cycle of the graph. The other portions of the graph, again, we realize this is periodic, so there. And you can again kind of see how this goes. All right. So we have those again points. Now let's see. We have the graph of this thing, and that's about it. I mean, that's all we want to know is just the general form. So that's the graph of cotangent, one cycle of it. Let's take a look at the graph of secant now. And the secant function, that would be y equals secant x. As a ratio identity, that's the ratio of 1 over cosine x. So let's begin again with our domain and vertical asymptotes. The vertical asymptote is placed where the denominator is 0. That means all x, so that x is equal to pi over 2 plus k pi. Right? Those are the zeros of cosine. They become the vertical asymptotes of the graph of secant. Therefore, domain is going to be everything but those. X such that x cannot equal to the vertical asymptotes. See how that works? The zeros or x-intercepts. Well, because I have a fraction, the only way a fraction can be 0 is if the numerator is 0, but then the numerator is 1. 1 can never equal to 0, right? Therefore, this one, none. There are no x-intercepts, no zeros of the basic secant function. Now, there will be zeros of secant that is shifted maybe in a vertical direction, up or down, to cause it to create an x-intercept. But its most basic form, just secant x, does not have zeros. The other thing, or the other basic thing, is for the period. Just like tangent, the period is 2 pi, just like cosine. And going back here to cotangent, I didn't put down the period of cotangent is pi, just like tangent. That one is just like tangent. Yeah, I did mention the period is pi. All right. The secant function is period is just like cosine is 2 pi, and we talked about the domain, the zeros. Oh, the range of this, we get it in a moment. I'll show you on the graph again, but we did this range earlier when we first discussed the secant function. Negative infinity to negative 1 and 1 to infinity, including 1. Okay, now what does the graph of this thing look like? Let me bring the graph for you. And here you go, a nice graph of this. so I don't have to do it by hand. You get a better graph when I copy it from the textbook. So here you go. Again, what you see in black here, and this is a very common way, by the way, in trig textbooks to do this, because again, we view secant as the reciprocal of cosine. So what happens is, there you go, this is the graph of cosine. Okay, so you're looking at that, the graph of cosine. And if you take the reciprocal of these, well, this point is reciprocal will be that. The reciprocal of something near 0 will be infinity. The reciprocal of 1 is itself. And what else? On this side, the same thing. As you get close to 0, notice 1 over 0 is undefined. So the graph goes to plus minus infinity, depending on whether you approach the 0 from the right or approach it from the left. Okay. The actual graph that we want is the blue, the graph in blue here, which let me show you. This is the actual graph. And here, this will be one cycle. There you go. That will be like one cycle of the graph of secant, the graph of secant. And again, in a few minutes, I'll show you how to graph a typical secant function. Okay. But keep in mind that we have one cycle between negative pi over 2 and right in here, 3 pi over 2. The distance from here to there is 2 pi. So that would be one complete cycle right there. Okay. And there you have it. So I'm going to just keep this one. Let's talk about cosecant now. Cosecant, again, as a ratio identity. For cosecant x, we can think of cosecant as the ratio of 1 over sine x. And we get the graph by doing exactly what the graph of cosine, how it helped us get the graph of secant. We're going to do it the same way using sine. Now, first of all, the period of cosecant, just like secant, sine, and cosine, the period is 2 pi. That means one complete cycle, which means it takes 2 pi interval. Zeros, well, there are none, because the numerator is 1, and that fraction can never be 0. So zeros are none. What about vertical asymptotes? Vertical asymptotes are places where sine is 0, right? Denominator is 0. So that's going to be k pi. That's the vertical asymptote. And that in turn defines the domain of the function. The domain of the function is anything but the vertical asymptotes, right? Places where we have a vertical asymptote. The range of this one is just like the range of secant from negative infinity to negative 1 union 1 to infinity. All right. Oh, and I didn't show you here. This is where the range is for secant. You see that? It goes from 1 to infinity. And then it goes from negative infinity to negative 1. Right? From the way down here to up here. So that's going to be the range. All right. We're going to see that similarly on the graph of cosecant. We're going to see the same thing on that graph. All right. So I have the vertical asymptote, domain, period, range, and we mentioned there are no zeros. Perfect. So let me now bring the graph of cosecant here for us. And there it is, the graph of cosecant. So now we get the graph of cosecant by taking the reciprocal of the graph of sine x. So sine x is actually this one. This is the graph of sine x. So if we take the reciprocal of sine, we get the blue curves. Okay. And the blue curves, that would be this portion of the graph and this portion of the graph, and so on and so forth. It'll just go like that forever, right? That'll be the graph of cosecant, the reciprocal of sine. And you can see now again that there is no x-intercept for the graph. That's why we said the zeros are none. And we can see that the range goes from 1 to infinity on the positive side. And it looks like it's going from -1 to -infinity, right? But then in interval notation, we write the smaller on the left, larger on the right side. That's why the range is what it is, the way we have. Okay, and there you go. So again, important, very important to recognize where one cycle occurs. So for the basic cosecant function, the vertical asymptote is at 0, right? And 2 pi. Those are the two vertical asymptotes. In between, we have one complete graph. There we go. We have one cycle of the cosecant function. And there you've seen now all 4 of the trig functions in this section, with the tangent, cotangent, secant, and cosecant. Now let's take a look at some examples and see how I actually graph these without plotting any points. Let's say I want to graph. Let's start with tangent. We did a tangent, and we did tangent of x. So let's suppose we do tan of pi over 2x. Again, the period, the formula for period is 2 pi, or for this one, sorry, it's pi over 2. This number, the coefficient on x. So the period is 2. You can invert pi over 2, you get 2 over pi. That's how you get the 2. All right, so period is 2. We'll get that period in just a moment in another way as well. So here's how we want to graph this one. And then we'll find all these zeros, all the vertical asymptotes, range, domain, and everything that we talked about the other one. And we will graph it indeed. So here's how I do this. I want to know where one cycle is. Remember, one cycle of tangent, let me go back up here. One cycle of tangent occurs between -pi over 2 and pi over 2. Those are the vertical asymptotes. So I'm going to do the same thing. I'm going to set pi over 2x between -pi over 2 and pi over 2. I want to know where the starting and the ending of that graph is with the asymptotes. Now, to isolate x, multiply everything by the reciprocal of pi over 2, which is 2 over pi. And this way we get -1, x, and 1. So we get one complete tangent wave between -1 and 1. This is the start again, and this is the end of one cycle. And remember, those are the asymptotes. So check this out, how quickly and easily I'm going to graph them. I'm going to graph my basic tangent. See that? And I'm going to label my coordinate system. This should be x equals 1. This should be x equals -1. There's my 0. So it looks like the 0 hasn't changed, the x-intercept. But we'll verify that. So this is the graph. Okay, we're done with the graph of it, one cycle. Let's do the vertical asymptotes. Okay, so remember, the vertical asymptotes are zeros of cosine, right? Because tangent is sine over cosine. So what I'm going to do is I'm going to set pi over 2x, the argument of tangent, equal to place where cosine is 0, pi over 2 plus k pi. All right, and this will give me all the vertical asymptotes. Now, to isolate, multiply everything by 2 over pi on both sides. So we get 1 plus k pi times 2 over pi is just 2k. Now, 2k plus 1, remember k is an integer. 2k is always even, isn't it? Multiply by any integer, 2k would be even. When you add 1, 2k plus 1 therefore is always odd. So what this is telling me is that the vertical asymptotes occur at odd numbers. And there you go, -1, 1. The next one will be at 3, 5, 7. On the positive side, -3, -5, and so on the negative side. There's your vertical asymptote. Domain is going to be exactly that, except we don't allow vertical asymptotes. So I'm going to go x such that x cannot equal to a vertical asymptote. There. That's the domain. The range is intact. The range isn't going to change here. Range is -infinity to infinity. Okay, what else? Zeros, the x-intercepts. Very important. Zeros are the x-intercepts. And the zeros are zeros of tangent. The zeros of tangent are zeros, the same as zeros of sine, because the ratio identity sine to cosine. So the zeros, I'm going to set again pi over 2x, the argument of tangent, equal to k pi, which is the zeros of sine. And that was also, by the way, the zeros of basic tangent also, wasn't it? See right here? So you set them equal to the characteristics of the basic tangent. And what are we going to get here? Multiply both sides by 2 over pi, and you get k pi times 2 over pi, 2k. Wow, 2k is even, right? If k is integer, twice any integer is even. And there you have it. So the x-intercepts occur at when k is 0. The next one is at 2, 4, 6, 8, and so on. On the negative side, it's going to be -2, -4, -6, and so on. And there you have it, all the characteristics of this function. Sounds cool. Next, let's take a look at, how about the cotangent? Let's do a cotangent. I did tangent. Let's do cotant. So in this example, we want to graph and get all of the specifics for 3 cotangent of 1/2 x. The period of this one, the period is pi over the coefficient over 1/2, or simply 2 pi. And again, you can get the period also by looking at the length of that interval, the interval that we set up for the vertical asymptote. The distance in this case, my previous example, from -1 to 1 is 2 units, isn't it? That distance from here to there is 2, which is exactly what the formula for the period told us. Now, let me do this one. The vertical asymptotes for cotangent, because cotan again is the ratio of cosine to sine. So the vertical asymptotes are zeros of sine. That means I set 1/2 x equal to k pi, multiply everything by 2, so we get 2k pi. And there you have it. So these are multiples of 2 pi now, right? Multiples of 2 pi. So when k is 1, we get 2 pi. When it's 2, 4 pi, 6 pi, 8 pi. When k is negative, we get -2 pi, -4 pi, -6 pi, and so on. So those are the vertical asymptotes. Thus, the domain of this function is going to be all x, so that x may not equal to 2k pi. What about zeros? Zeros are x-intercepts. The x-intercepts are places where the numerator is 0, the zeros of cosine. So I'm going to set the argument of my function, cotan half x, equal to the zeros of cosine, pi over 2 plus k pi. Then double up on everything, both sides multiplied by 2, we get pi plus 2k pi. Okay, and there you have it. And of course, you can factor the pi if that's what you would like to do. You get 1 plus 2k, which is, these are odd numbers, right? 2k plus 1 is odd. So you get odd multiples of pi. So it's going to be pi, 3 pi, 5 pi, 7 pi, and so on. Those are the zeros. And let's see, how about one cycle? Where is one cycle of this cotangent? So I'm going to set it, again, argument of my cotangent was 1/2 x. I'm going to set it between 0 and pi, because that's where one cycle of cotangent was, right? Right in here, between 0 and pi. Good, and let's see, this is easy to solve. Multiply all parts by 2, so I get x is, there you have it. That gives me the start, again, starts at 0 and ends at 2 pi. Now I can actually graph simply one cycle from 0 to 2 pi. So this is going to be the x, and suppose my, again, vertical axis, sorry, there's my vertical axis, which is x equals 0, the y-axis, and the other one is at 2 pi, call this 2 pi, x equals 2 pi. Again, these are dotted because these are the vertical asymptotes. Find a halfway and just draw your cotangent. There you have it. Okay. And if I want to graph them more accurately, I can always maybe use a software or something. And there you have. That is one cycle of this cotangent wave. All right. And oh, what about 3? It's like I did nothing with the 3. The effect of 3 is actually this. Let's say my cotangent is flat and rising like that. Then what that 3 times do to it is it triples the ordinates, right? So this point is up here, this point is up here, this point is up here. So it gives it this kind of a look because the ordinates are 3 times the size. So let me actually maybe show that on my graph on how is this going to work out. Again, if this is just my basic cotangent like that, now cotan 3x is going to look more like this. There, you see that? And there you have it. So that's the effect of 3 in front of it. If that was -3, you simply reflect it about the x-axis. All right, let's take a look at secant. Just a couple more here, folks. One for secant and one for cosecant. This next example, suppose I have y is equal to 4 secant, and let's go secant of 1/2 x. All right. Now, remember, this could be viewed as 1 over cosine of 1/2 x. True? Because of that reciprocal relationship between secant and cosine. Now, let's find the vertical asymptotes of secant again. The vertical asymptotes are places where denominator is 0. Okay, so we want to find the zeros of cosine 1/2 x. So I'm going to set 1/2 x equal to the zeros of cosine. Multiply everything by 2 plus 2k pi. And there you go. We can factor a pi, of course. And we get 1 plus 2k, which means this means odd again. So we have odd multiples of pi. That's pi, 3 pi, 5 pi, and so on. Positive, and then, of course, the negative ones as well. And those are the vertical asymptotes. Oh, the period of this thing, the period is going to be pi over 1/2 or 2 pi. But then we get that from our interval as well. Now for zeros, this one again, remember the only way this can be 0 is if the numerator of the fraction is 0, which is 1, never zeros. So none, there are no zeros of this one, no x-intercepts. So let's graph one cycle. What does the one cycle of secant looks like? Let's go back to our graph of secant here. Secant was 1 over cosine. And there you go. Remember, we mentioned secant, you get 1 cycle of secant. Right here. Between negative pi over 2 and 3 pi over 2 is when we get one of these graphs. Negative pi over 2 and 3 pi over 2. Okay. Between those two numbers. So that's what I'm going to do. Therefore, I'm just going to set 1 cycle between negative pi over 2 and 3 pi over 2 for the basic secant function. And the secant I'm working with is half x. So we're just going to set half x equal to that. And then isolate x, which is easy to do for this one. We're going to multiply all 3 parts by 2. Double up on everything. So that means this becomes negative pi, then I have x, and then I have 3 pi. All right, so 1 cycle of what we saw is going to happen between negative pi and 3 pi. Okay, and here it is. So this is 3 pi. And this one is, well, let me be a little more accurate here. I'm going to make, there you go. Let's say this is negative pi. So 3 pi, I need to go a little further here, a little further out. And that's going to be 1 pi, 2 pi, 3 pi. A little more realistic. Okay, so we got those. Now, this is x equals 3 pi. 1, 2, 3, 4. So right in here, this would be pi, correct? Each tick mark is pi units, right? So this is pi. So I'm going to have another vertical asymptote here. X equal pi. All right. And when x is 0, notice right in here, secant of 0 is 1, so you get 4. Instead of starting at 1, you actually start at 4. Let's say this is 4. So I'm going to get one of these. Looks like a parabolic graph. And there you have it. So that would be one portion of that graph, and then the other part is going to be right about here. And there I have one complete cycle. And there you go. The coordinates of the low point up here is going to be 0, 4. The coordinates of the high point in the next portion of the cycle, right in here, is going to be 2 pi and negative 4. And this is at negative 4. Okay, and I can actually label these. That's 2 pi and negative 4. And this one is going to be 0, 4. All right. And there, you see how easy it is to graph these? Oh, and the range, let me put the range on this one. The range is going to be, for the positive side, it's going to go from 4 to infinity. And on the negative side, it's from negative infinity to 4 to negative 4. There. And that should do it. Perfect. So we got all the relevant information. Again, we're interested in zeros and the vertical asymptotes primarily. And that's for the secant. Let's finish this off. Let's finish this work with the graph of cosecant. So this way I've done one of every one of these. Y equal cosecant of, let's say I'm going to go 3 pi over 2x. Now if you note, none of the ones I have done or we have looked at in our examples involve a phase shift. We'll look at phase shift next. That will be our last section for this review chapter of trig functions, sine, cosine primarily. Okay, now cosecant reciprocal identity, that's 1 over sine of 3 pi halves x, correct? So here we go. The vertical asymptote. Vertical asymptote, it's going to be a place where you divide by 0. That means zeros of sine. 3 pi halves x is equal to k pi. See, when denominator is 0, you have division by 0 undefined, and hence vertical asymptote. Multiply both sides by the reciprocal of 3 pi over 2. That's 2 over 3 pi to isolate. 2 over 3 pi times k pi. The pi's cross out, so that's just 2/3 k. 2/3 k. Those are the vertical asymptotes. Therefore, the domain is going to be all x, such that x may not equal to 2/3 k. Good, we got that part. The period. If you want to use the formula for the period for cosecant is going to be 2 pi over the coefficient over 3 pi over 2, and that's just the pi's cancel, so you get 4/3. That means in an interval of 4/3 you have a complete cycle. Did we do the period up here? Yeah. Oh, the period of secant, sorry, I didn't do this right. It's 2 pi, because secant is reciprocal with cosine, right? So it's going to be the same. Sorry, only tangent and cotangent are pi. Go back up. Yeah, I did that one right. Sorry about this. So it's going to be 4 pi. Notice, by the way, it didn't affect my graph because the way I did this. I should have caught it here too. See, the distance from negative pi to 3 pi is 4 pi. And that is distance from here to here. That's 4 pi. That is a period. I'm glad I came back up. Look, I'm sure many of you caught that. All right, so there you go. 4 pi. Doing it correct for this one is 2 pi over 3 pi over 2. That's going to be 4/3. All right, 4/3. Now, zeros again, because the numerator is 1, so there are no zeros of this one, no x-intercept. Zeros are none. And what else? 1 cycle. Let's do 1 cycle, and then from the graph I get the range. For 1 cycle, again, I'm going to set it equal between 0 and 2 pi. Why? Let's go back to the basic cosecant. This is cosecant. Remember, we had one unique graph between 0 and 2 pi. Those were the vertical asymptotes. So let's see, where are those vertical asymptotes now? All right, and I'm going to go 0. The argument of my cosecant is 3 pi halves x. 0 and 2 pi. Okay, multiply all 3 parts by the reciprocal of the coefficient on x, which is 2 over 3 pi. 0 times that is 0. 3 pi over 2 times 2 over 3 pi, reciprocal multiplies to 1. And I'm multiplying 2 pi times 2 over 3 pi. That would be 4/3. Again, the period is the length of that interval, which is 4/3, which is exactly what we got here. Good, got the period. Now, let's do the graph. A complete graph happens between 0 and 4/3. So this is x equals 0. And then remember, we're going to have what, 2 parts. Here's one part. Here's another part. Correct? Oops. There you go. Okay, the first one is 0, and then this one is the ending. This is the start, and here's the end. It's going to end at 4/3. All right, in between 0 and 4/3, that's 2/3. That's half of 4/3, which is 2/3. So the other asymptote is at 2/3. And in between is when we're going to have each of those parabolic segments. And this one starts at 1. So right in here, call that 1. And halfway through. There, that's portion of it. And the other portion would be here. 1, 2, 3, right there. And we get the other part of this cosecant function. You can go back to the graph of cosecant. It looks just like the graph of cosecant. You see that? It opens up, then down. And that's what we have. The low and high points here right away. This point is 1, the y component of the point, and here the y component is -1. There's 0. Okay, halfway between 0 and 2/3 is when the low point is. So half of 2/3 is 1/3. This is 1/3. Each tick mark is 1/3. So it's 1/3, 2/3. This would be 3/3 or 1, and this one is 4/3. Got it. So I can label these points now. This point is going to be when x is 1, y is -1. And this point is when x is 1/3, y is 1. See how that works? And we can finish this off with the range now, because I have the graph. The range is going to go from 1 to infinity. On the positive side, the union from really it looks like -1 to -infinity, but remember we always put smaller number on the left, the larger on the right side. So it's -infinity to -1. And we have all the information we wanted about this function. Its graph, including the key information, such as vertical asymptote and zeros. Okay, we're good. We are done with this lecture. And again, I'm not sure how you are used to graphing these, but notice I did not plot any points in that. I didn't create a chart like this. That's not how you want to do it. And with that, we are done with this lecture. Okay, again, thank you all for watching, and until the next lecture.